नमस्कार बच्चों, मेरा नाम धन्या और हम लोग ग्रेड 11 केमिस्ट्री का सेकंड लेसन डिस्कस कर रहे हैं जिसका नाम है एटॉमिक स्पेक्ट्रम. एंड इन द लास्ट वीडियो वी लर्नड अबाउट द बोर्स मॉडल ऑफ एटम. नाउ टुडे वी विल बी लर्निंग अबाउट एटॉमिक स्पेक्ट्रम. Now first, what is a spectrum? Now suppose I take a prism. Okay, I take a prism and I allow the white light to pass through it. You can see a band of colors okay, and this band of colors that is obtained is called as a spectrum. It happens because of splitting of light, white light into different colors, the Vibgyor colors. Okay, now this is also called as a continuous spectrum. If you see all the colors or waves, it is called as a continuous spectrum. Okay, now suppose in case I take any gas particle and I heat it and I allow the light to pass through it. Sometimes it happens that maybe I will not get all the colors. Maybe I'll get only some shades or some waves or some energy waves. Okay. If I get only some energy waves or some colors, it is called as, that means few colors were missing. This is called as line spectrum or discrete. Discrete means it's not continuous. Okay. Some colors were missing. Maybe suppose I get only the blue color or only the blue shades, maybe blue, indigo, violet, only that shade I get and rest everything is missing. Okay, so if I don't get all the colors, it is called as line spectrum or discrete spectrum. Okay, now Bohr could explain this discrete spectrum or line spectrum. Okay, now this was the explanation. Now, in the last video, we saw the energy of different energy levels, right? So this was the first shell, and it had the lowest energy, minus 13.6 electron volts. Second one was minus 3.4 electron volt. The next one was minus, the third shell, minus 1.5 electron volt, and so. Okay, students, these are the energies of different orbitals. Okay, now on heating the gas, the electrons, if they get the sufficient amount of energy, they can move to the higher energy levels. Okay, so that we saw that in the last video too. Okay, so if they get the energy matching with the energy levels, they can move to the higher energy levels. Okay, now the electron always is stable when it is in the lowest energy level. So that means if they lose energy, they can return back, okay, in the form of, they can return back to the lower energy level. And when they return back, they will emit radiations. Electrons cannot be in between the orbitals. It has to be in the orbital. That means it has to absorb the amount of energy that matches with the energy levels, and then only it can jump. If they don't receive that energy, they won't jump. And similarly, the electron is more stable when it is in the lowest energy level, and when it is returning back to the lower energy level, they give off radiations. Okay, that means certain fixed amount of energy waves are emitted, or some colors. That means if they get an energy, or when they suppose the electron is in the second orbital, okay, and if they lose energy and return to the first orbital, That means energy has to be matching with the first energy level, right? So that means, students, only some particular waves are emitted that depends upon the difference in the energy level. Okay, so that means some fixed energy waves are emitted. Okay, it cannot absorb or emit any amount of energy. It emits or absorbs only fixed amount of energy that matches with the energies of the orbitals. Okay, so when the electron loses energy and it returns back to the lower energy level, the spectrum that is formed is called as emission spectrum. It gives out radiations, and the spectrum that you get is called as emission spectrum. Okay, now suppose you have, let's do a question on this. So student, I hope discrete and continuous and line spectrum is clear, and also the emission spectrum. So emission spectrum is nothing when the electron comes back to the lower energy level, it gives off radiation, and the spectrum thus obtained is called as emission spectrum. Okay, so let's do a question. An electron in hydrogen atom jumps from higher energy level N2 to lower energy level N1. Okay, so we need to find the energy. So that means it loses energy and comes back to the lower energy level. So you have to find the energy and wavelength of the emitted radiation. So we just saw that radiations are emitted when they return back. So you need to find the wavelength and the energy of the emitted radiation. So it is, so from this picture, this is the second energy level and this is the first one. Okay, now it is jumping from N2 to N1, right? So when it is jumping from N2 to N1, it will give off radiations. So we just said it will be, the energy will be equal to the difference in the energy levels, E2 minus E1, right? Now, this is E2 means the energy level of N2 minus energy level of, that's why no, it's not, okay. Now, over here, we remember the expression for energy for the nth shell. Minus 13, I told you it's important, you need to memorize it, times z square, where z is atomic number, by n square, where n is the shell number. And here we have z equal to 1 because it's hydrogen, and n values we already know, 2 and 1. Okay, now so over here, delta E equal to minus 13.6 times 1 by 2 square minus, so E2 minus E1, right? So minus of minus 13.6 times 1 by 1 square. So this comes to be equal to 10.2 EV. So that's what we said, that when the electron is jumping from the higher energy level to lower energy level, the energy emitted is equal to the difference in the energies of the two energy level. So the spectrum thus obtained is called the emission spectrum. Okay, so this is the difference of the two energy level. Now, our question is not over. We still have to find the wavelength. Okay, that's our next part of the question. Okay, now students, I hope this is clear. You need to memorize this term for energy that we derived last time. Okay, now coming to the wavelength. Okay. The wavelength now, energy is equal to hc by lambda. Okay. The energy expression is given by hc by lambda, where c is the velocity, lambda is the wavelength, h is the Planck's constant, and E, that means delta E, is the difference in energy of the two energy levels. Okay, now over here we already know the value of delta E, which is equal to 10.2. Okay, so this is the expression for the energy. Okay, now this is the energy, this is an expression for the energy of the wavelength, where lambda is the wavelength, c is the velocity of light, h is the Planck's constant. Now, this 10.2 that we got was an EV, electron volts, right? Now, which is equal to, I'm putting the value 6.636 times 10 raised to minus 34 joules second times velocity of light, I hope you will be knowing, 3 times 10 raised to 8 meter per second by lambda, that is our unknown value that we need to find out. Okay. Now here, the value of Planck's constant is in joules per second. Now we need to convert, if I use this, I need to convert this, convert the value of energy into joules. So instead I use the shortcut method, which will be helpful for the competitive exam. Energy in electron volt is given by 12375 by lambda, where lambda is in Armstrong. Okay, so please memorize this. This is a shortcut method and you can easily find out the value of energy. Now you know where E is delta E, the difference in energy level, which is equal to 10.2 EV. Now substitute the value. You will get lambda is equal to 12375 by delta E. 12375 by 10.2 EV. You get lambda equal to So student, this is the value of lambda you get. Okay. So this is very important. So please remember this formula so that it's easy for you to find out. Okay. Now, moving on further, okay, students, suppose an electron is jumping back from energy level 2 to energy level 1. Okay, suppose this happens, and the difference in energy we all know is given by E2 minus E1, or En2 minus En1. Okay, and we also saw delta E is given by hc by lambda. This is the energy of the wavelength. Now, if I substitute the values minus 13.6 times z square by n2 square, we just did this formula now, right? Minus 13.6 times z square by n1 square. Okay, taking minus or taking 13.6 z square common, I have 1 by n1 square minus 1 by n2 square. Okay, now here what I'm going to do is I'm going to divide and multiply by hc by lambda. So what I'm going to do, divide and multiply by hc by lambda. Okay, why I'm doing this, I'll tell you. Just hold on. Okay, so hc by lambda sorry. So students, what I'm going to do next is divide and multiply by hc. Why I'm doing this, I'll tell you. So hc by lambda is equal to hc times 13.6 z square by hc. So see, I have divided and multiplied. Okay, rest of the terms remain the same. 1 by n1 square minus 1 by n2 square. Okay, so I can cancel the common things. Okay, now what I'm going to do is 1 by lambda equal to 13.6 by hc z square by 1 by n1 square by 1 by n2 square. Okay, and this particular value is our new constant, which is called as Rydberg constant, R. Okay, so I have the wavelength for the atomic spectrum, that is 1 by lambda, is equal to the Rydberg constant is R, z square by 1 by n1 square minus 1 by n2 square. Okay, usually the value of R is given, you don't have to memorize, so just keep it in your mind. 1.09 times 10 raised to minus 7 per meter. No need to memorize. Okay, so I'm just telling you. Okay, so we can, from this expression, if the Rydberg's constant is given and you know the value of n1 and n2, 1 by lambda can be calculated. Okay, so this is the expression for the wavelength. Okay, now students, coming to this jumping of electron from n2 to n1. Okay, now this jump is from a higher level to a lower level, right? So it will emit the radiations, right? So this equation only I'll keep, okay? I'll keep this equation here. I will be needing this equation, okay? Now, students, suppose I have n is equal to 1, okay? This is n is equal to 2, n is equal to 3. The gaps are decreasing, okay? The gaps will decrease. It's like that. N is equal to 4, etc. until n is equal to infinity. Okay. Now, so these gaps will reduce. So as you move up, you studied that the energy is increasing, right? So as you are moving up, the energy of the orbits are increasing. Okay. Now, when the electron jumps from N2 to N1, N3 to N1, N4 to N1, etc., from infinity to N1, all of them, whenever the electron is jumping from a higher energy level to N1, okay, we get a spectrum which is called as Lyman series. So Lyman series. So students, when the electron is moving from infinity to N1, N2 to N1, N3 to N1, N4 to N1, from higher energy level to N1, the wave is called the Lyman wave and the series formed is called the Lyman series. Okay, so when N2 can be 2, 3, 4, etc. and when N1 is 1, what is the wave we get, or what is the series we get? We get the Lyman series. This is very important. And where is it? Where it is found? In the ultraviolet region of the spectrum. Okay, so this Lyman series, where do we find it? Ultraviolet region of the spectrum, which we cannot see. Okay. Now, from here, if we calculate, suppose, calculate lambda when the electron jumps from n is equal to 2 to n is equal to 1. Okay, so we use this formula. That's why I just kept it there. So 1 by lambda is equal to rz square by, what is n1? 1 square minus 1 by 2 square. Okay, we have 1 by lambda equal to, and z is equal to 1 because it is, suppose it is hydrogen. Okay, it is for hydrogen atom. Okay, so I have r 1 minus 1 by 4, which is equal to r 3 by 4. This is 1 by lambda. Okay, students, because I have the formula over here, I'm just rubbing this off. Okay, now, students, please remember one more information. 1 by r has a value of 911 Armstrong. Okay, please remember, it will be this. You can remember, this will be more easier. Okay, so I have here lambda equal to what? 1 by r times 4 by 3. Now I know, remember this value of R, 1 by R value rather than R equal to 1 point something, that one value, remember this value, okay? So this is 911 times 4 by 3, which is equal to 1216 Armstrong, okay? So students, the value of wavelength when the electron jumps from n is equal to 2 to n is equal to 1 is 1216 Armstrong. Okay, now moving on further. Let's find out the value when the electron jumps from infinity to n1. Okay, now here we have one by lambda is equal to rz square 1 by n1 square minus 1 by n2 square. Okay, so 1 by lambda is equal to, for the same hydrogen atom I'm discussing, so Z is equal to 1. So 1 by lambda R1 square by 1 by 1 square minus 1 by infinity square, which is equal to 0. So 1 by lambda is equal to R. So R is equal to, lambda is equal to 1 by R, which is equal to 911 Armstrong. So this is from infinity to 1. So you can see, students, the value of lambda is more for small transitions. Small transition means N2 to N1, N3 to N1, N4 to N1, all those values are small transitions. All those transitions are small transitions. The value of lambda is more. But when the value of, when the transitions are big, for example, infinity to N1, all those, the wavelengths are smaller. So we can say small transitions or small wavelengths comes from big transitions. So we have proved that. So, and vice versa. So if we have a bigger transition, the wavelength is small, and vice versa. Okay, and another thing, please remember the value of 1 by R. Okay, now students, moving on further. Students, we just saw that the Lyman series lies in the ultraviolet region, and we cannot see it. Okay, it is not in the visible area. Okay, now if the electron jumps from n is equal to 3, I'll show it with another color, maybe green. Okay, n is equal to 3 to n, n2, n4 to n2, n5 to n2, etc. from n infinity to n2. Okay, then if the series formed is called as Balmer series. Balmer series. Okay, so whenever the electron is moving or jumping from higher energy level, so N2 can be 3, 4, 5, etc. and N1 can be 2. And what series do we get? Balmer series. And this lies in the visible region. Okay. Similarly, if we have, I'll take another color. The electrons jumping from higher energy level to N3. Okay, so N2 can be 4, 5, 6, etc. unto infinity. And N1 has to be 3. We call it as Paschen series. And this lies in the infrared region. Infrared region. Okay. The Balmer series is visible because this lies in the visible area. Okay. Now, similarly, if the electron is moving from higher energy level to N4, okay, so N1 is 4 and N2 can be 5, 6, 7, etc. until infinity. We get yet another series called the bracket series. And this also lies in the infrared, IR. I write it as IR, infrared. Okay. So these are the series obtained when the electrons jumps from higher energy level to, if it is jumping to N1, we get Lyman series. If it's jumping to N2, we get the Balmer series. If it is jumping to N3, we get Paschen series. It is jumping to N4, bracket series. Okay, we have yet another series called the Fund series when it is jumping from high energy level to N is equal to 5. It is called as Fund series. PFUND, Fund series. Okay, this also lies in the infrared region. Okay. So you can see that the electron can come from higher energy level to lower energy level, and it will give you the different series based on to which energy level it is coming. Okay. Now, before we move, okay. Another thing which I want to share is okay, students. Suppose we have an electron in the maybe N1, N2, N3, N4, etc. Suppose we have an electron in the 4th energy level and it loses energy and suppose it's moving to the 1st energy level. Okay. Maybe the electron can directly jump from N2 to N1. Sorry, electron can directly jump from N4 to N1, or it can jump to N3 and then to N2 and then to N1. Okay, several types of transitions are possible. So there is a shortcut if they ask you to tell the number of transition, okay, or the number of spectral lines. So we can determine the number of spectral lines by the following formula, which is very helpful. N2 minus N1, N2 minus N1 plus 1. This is just a shortcut formula, please remember, by 2. Okay. this is just to check the number of spectral lines. Okay. Suppose in this case, N2 is 4, N1 is 1. Okay. So we have 4 minus 1 by 4 minus 1 plus 1 by 2. Okay. So we have 3, 4 by 2. This comes to 6. So how many lines or how many transitions are possible? 6 transitions are possible. So in case you get a question like this, it's a handy formula. Okay. So students, today we talked about the discrete and continuous spectrum, emission spectrum, and the different kind of series that we get when the electrons are jumping from higher energy level to lower energy level. Okay, students, so that's all in this video. Thank you. Have a great day.